Okay, thanks for introduction and thanks for the invitation. This is actually my first time to visit to India. And so recently I was writing some teaching statement for job applications. And one of my colleagues told me that there is one magic word that I need to include in my teaching statement, which is like active learning. And I want my lectures to be like active and interactive. So like if you have any question, please just like stop me and ask. Okay, so this is the plan of my lectures. So the basic idea of my lectures is kind of trying to like review some like old and new ideas about large N series, and especially discuss like how those ideas can be utilized in the context of integrability in a planar n equals 4 node series. And in the first lecture, I'm going to talk about rather old stuff, but it's actually like a not very much well appreciated stuff, which is about duality in lattice and matrix models. And so this is in the second lecture, I'm probably going to talk about baryons and determinants. And in the third lecture, I'm going to talk about my recent work about planar n equals 4 nodes. So this is the plan of the lecture today. So I'm going to first start with very basic Kramers-Wannier duality of Ising model, and then discuss some generalization of Ising model, which I would call ZPQ lattice model, and discuss the duality there, and then discuss the duality of this model, the relation between of the duality of this model and the T-duality in the string theory. And finally, I discuss some like Ising model on the random lattice and Kramers-Wannier duality. And that final topic kind of connects to the topics of the second lecture. Okay, so this was the plan. This is the plan, and let's start. So let's start from Kramers-Wannier duality. So Kramers-Wannier duality, as you all know, is a duality in Ising model. And so the model that I'm going to, so let me just write down the model explicitly. So I'm going to talk about Ising model on a square lattice. So you have a lattice which is of a square shape. And then for each vertex of this lattice, there is a spin degrees of freedom, which takes either +1 or -1. And I want to discuss the partition function of this Ising model, which is basically sum over all possible spin. And there is a Boltzmann factor, which is exponential beta, which is the inverse temperature, times this factor, which is basically just the product of spins on the neighboring sides. And the sum is basically sum over links of this graph. So this is the definition of the model that I'm going to talk about. And so let's just call this graph or lattice gamma. And as you know, as you probably learned in statistical mechanical course, there is a two nice expansion of this partition function. One is the high temperature expansion. So the high temperature expansion can be derived in this way. So you take this Boltzmann factor, which is e to beta si dot sj, then you can of course see that this just take e to plus beta when si dot sj is +1, and e to minus beta when si dot sj is -1. But the point is that you can actually write it in this different way, which is like a cos beta plus sinh beta times si dot sj. And you can easily check that these two are the same. And if you use this description or expression, then you can rewrite this partition function in this way. You have cos beta to an L. Let me just first write the expression and then explain what it means. And then I have a product over links, and which is 1 plus tangent hyperbolic beta si dot sj. So this NL is just a number of links, the number of edges in the graph. Okay, so this gives you a nice high temperature expansion which is valid when beta is very small, because when beta is very small, this factor is very small. So basically, when beta is really 0, you just need to take 1 from everywhere. And if you want to have an expansion, you just pick like some numbers of this factor. And typically, if you do the expansion like that, then finally you get some like a series of product of S's, and then you just need to do the summation over Si's. So this is how the expansion works. And what is further nice about this expansion is that you can rewrite this expansion as a sum over loops that you can draw on a lattice. So the reason is as follows. So if you consider, so as I said, the expansion gives you the product of spins, but we know that in the end we need to sum over Si equals plus 1 and minus 1. So if, for example, there is only, so let's say you have some lattice, and then for each product is associated with the links. So let's say you just keep this one, contribution from this one, so which means that you basically pick this one for this lattice, for this link, and for others you just pick 1. And that gives you S1.S2, where S1 is here, and S2 is here. But that contribution is just 0, because if you sum over plus 1 and minus 1, it cancels out. So this basically means that if you draw this kind of picture, then you always need to, if you have this, if you pick this link, you also need to pick some other links like this, so that S1 cancels out. And the same applies for other vertices as well. And if you think a little bit about it, then you can easily convince yourself that all the configuration that contribute in the final sum is the one in which you have like a closed loop on the lattice. So this gives you an expression that the partition function is basically given by sum over all possible closed loops on this lattice. And for each loop, I just get this factor, where LC is just total length of the loop. So if I were to draw some configuration that contribute to this sum, then it's going to be something like this. You draw some loop here, and you draw some loop here, and you can even consider some loop like this. Okay. So in this way, you can basically convert the sum over spins into sum over loops on the lattice. So this is the well-known high temperature expansion. And on the other hand, on the other edge of the parameter, which is the low temperature, you can also have expansion, which is organized into a sum over loops. So let's discuss low temperature regime. So in the low temperature regime, we know what we expect. because we are considering ferromagnetic Ising model. Basically, if you really lower the temperature, then the Ising spins wants to align. So the dominant configuration when beta is infinite is, of course, this configuration where the spins are all up or all down. And if you decrease the temperature a little bit, then typically the configuration that's important is given by some cluster of down spins and lower up spins. So let's say you draw some cluster, and inside this you have a down spin, and outside you have up spin. So this is the an example of configuration that contribute at low temperature. And so you have some two clusters here, and then here there is a domain wall separating two clusters. And so this kind of configuration basically gives you yet another expansion in terms of loops, because now you have some domain wall which forms a loop on a lattice. And that gives you expression, which is basically something like e to beta times, again, n times L. And then you sum over all possible loops. But now the loops are drawn on a dual lattice, because the vertices of these loops are basically the faces of the original graph.
The vacuum is that everyone is parallel.
Sorry?
Is that the vacuum?
No, this is not a vacuum. Of course, the vacuum is up.
Everything is parallel?
Yeah.
Don't think
You mean here?
Yeah.
Well, because okay, so yeah, this is actually the correct sign, because I want a ferromagnetic one. So if the spins align, I want a bigger Boltzmann weight, right?
I see. Okay.
Yeah, actually, I've got confused when I was preparing lecture. So yeah. And then I have this expression for each domain wall. So again, this is the length of the loop, but now it's a domain wall. And if you have a domain wall, then there is exponential suppression. So this is the second expression, which is good in the low temperature regime. And you can easily see that it's better in low temperature regime, because in the low temperature regime, this factor is very, very small. Okay, and by comparing this expression, and if you just forget about these prefactors, then you can see that both high temperature and the low temperature are given by some expansion in terms of loops. And by comparing these two expressions, then you can conclude that there should be some duality of the Ising model, which is basically the self-duality of the Ising model, and that's precisely what people call Kramers-Wannier duality, which basically state that up to over all factors, so the Ising model at inverse temperature beta defined on the original lattice is equal to Ising model defined in a different temperature and defined on the dual lattice, where the relation between these two temperatures is given by tangent hyperbolic beta equals e to minus 2 beta twiddle. And the relation between the two is that this model you can expand in high temperature expansion, and that gives you basically the loops on the lattice, which is given by product of spins, whereas the same loop expansion you can also draw on this side, but the interpretation is different, And now you have some domain wall. And that gives an expansion in terms of loops. Okay, so this is a basic statement which you're perhaps familiar with about the duality of the Ising model. But I should point out that this duality is not actually precisely correct. So probably this part is not something that you learned in statistical mechanics, but the duality is not precisely correct, and you can see it if you consider the partition function on higher genus surfaces. In particular, for instance, let's consider Ising model defined on a torus and try to do the high temperature expansion for which, so this is the high temperature and this is the low temperature. And that gives you some expansion as a sum over loops. And in particular, on the torus, you can draw this configuration of loop, where a loop goes around like this. And then you have a lattice like this. Okay, so this is completely legitimate loop configuration, because here in the high temperature expansion, loop is just given by product of SIs, and this is one configuration that you need to include. However, if you want to interpret the same configuration from the low temperature expansion point of view, you are in trouble actually. So let's see what happens. So if you want to interpret it as a domain wall, then you have some loop, and then you have some lattice here. So the domain wall cuts the face of the lattice. And because it's domain wall, I want to put upspin on this side of the domain wall. So let's say on this side of the domain wall, and I want to put downspin on this side of the domain wall. But it's clear that it doesn't make sense because it's connected behind. This geometry is connected behind. So this is not good. So
the defect here, you can imagine the torus essentially coming from a plane with some cuts.
Mm-hmm. Yes. Yeah, right. Yes. Yeah. In order to make sense of it, you need to introduce some defect. Yes. Yeah, I'm basically talking about that subtlety. Yeah, but there is a, yeah, I think it's precisely the same as basically the same as what you said, but there is also kind of different resolution of this problem, and the resolution is that so to slightly modify the statement of the Kramers-Wannier duality. So usually people are familiar with the statement that it's the duality of, like a self-duality of the Ising model, but you can fix this problem by considering different model. But the point is that this different model is still defined on the dual lattice. So in that sense, it still preserves some features of the Kramers-Wannier duality, but now I'm just replacing the Ising model with some different model. So what is that different model? So this different model, so the resolution is to define link model in which which the degrees of freedom lives on a link rather than vertices. And the definition is given by this. So you define the twaddle of the link model, and that is given by this expression. So now, for each link, you have a variable m, which you have variable u, which takes value plus or minus 1. And then there is some slightly non-local constraint for each faces of the lattice, which it's almost gauge theory, yes, but yeah. And then I put this factor. So what I'm saying, okay, so but I need to explain what this means. So this means that, okay, so now the degrees of freedom is living on links. So for each link, you have degrees of freedom uij, and this delta function or Kronecker delta is defined for each face of this graph, and this for each face you just multiply the variable living on the edges of the face. So in this case, if you have u1, u2, u3, u4, then you just multiply 4 of them, and then require that it must be equals to 1. So now I perform the low temperature expansion to this model.
This model is very trivial to the plane.
Yeah, because of this factor. So if there is no factor like this, then it's really trivial. And because of this factor, you can, yeah, slightly non-trivial, and you can actually get the Ising. So on plane, if you put this factor, it's the same as the Ising model. Sorry, yeah.
That's this sort of chart.
Yeah. Yeah, so let me now try to do the low temperature expansion. So which of that model, which replaces this. So the low temperature expansion, so because of this constraint, so let me see. So U's are basically taking plus or minus 1. And because of this Boltzmann factor, the most preferred configuration is to set all U's to be plus 1 or all U's to be plus 1. And if you lower the temperature a little, if you increase the temperature a little bit, then some of the U's become minus 1. But because of this constraint, you cannot just arbitrarily put minus 1s on a lattice. So the allowed configuration of minus 1 of the lattices, for example, is something like this. So suppose you want to put minus 1 here, but this is not allowed because if you look at this face, then there is only one minus 1 here, and if you multiply everything, you just get minus 1. So I also need to put minus 1 here, and then I can also do something like this. And so this is one allowed configuration. You can easily check that this is okay, this face is okay, this face is okay, this face is okay, this face is okay, and this face is okay. And for each of these allowed configuration, you can basically draw a dual lattice, dual loop on a dual lattice like this by drawing some lines which intersect these yellow lines perpendicularly. And this gives you, again, sum over loops on the dual lattice, like in the Ising model. But this model is slightly better than the Ising model if you consider the theory on a torus, because in this model, this is completely allowed. Because you just need to, so this is just a configuration in which you pick -1 along, sorry, you pick, so let me just write here. So for this model, what was prohibited in the other model is allowed. So you have this, and then, so there are sorry, there are too many yellow lines. So I want the, yes, but I want this kind of loop, and this is allowed because I just need to choose -1 along these loops. So this is allowed. So now, with this model, I can basically correct the Kramers-Wannier duality. So now the statement is that instead of Ising model, I just have this link model here. So if you use the link model on the right-hand side, then everything still holds, even in like higher genus surfaces.
Also show this in high temperature
Mm-hmm.
model. You can get
Let's see, high temperature. Yeah, that's a good question, but I never thought about it. Yeah.
It's not self-worth. He's saying it's
Yeah.
no longer self-worth.
Yeah.
So in the IC model, in one expansion it was allowed, another expansion it was not allowed.
Right.
High temperature it was allowed, and
Yeah.
yeah. Expansion doesn't go.
Yeah.
So if you're dualizing it, then you should.
No, you're not dualizing it. I think he's saying that the low temperature, high temperature Ising is dual to the low temperature link.
And then low temperature Ising should be dual to the high temperature.
The low temperature Ising.
Yeah, perhaps. Yeah, but yeah.
At least okay. One phase it is dual.
Yeah.
Maybe
Yeah.
both phases.
Yeah. Yeah. But yeah, I didn't think about it, and I think I'm a bit too jet lagged to answer your question right now. So, so let me just avoid answering the question. So let me just give a couple of comments. So the first one is related to Spencer's comment. So on sphere, so locally, so there was some non-local constraint for the link model. Locally, this non-local constraint, which is can be solved by the following ansatz, which is you pick link and then just regard it as a product of two spins. And these spins take plus or minus 1. And if you do this replacement, then you can easily see that this precisely becomes the Ising model. But the point is that if you consider theory on a non-trivial Riemann surface, there is a non-local abstraction for defining the spin variable. So that's why it was better to actually discuss link model rather than the Ising model. But given this property that some spin model, which is defined on the lattice, on the vertices, can be dual to the model that are defined on the links, then maybe one might think maybe it might be better to consider models with both vertices and link variables. this is basically my motivation for introducing what I call ZPQ model. Yes.
Can I ask a question?
Yes.
It's by the credit lag. Very simple one. So when you write the packet like this, in a sense, it's saying that the field strength is pure gauge.
Right, right.
So therefore,
yes.
the dimension factor goes away.
Yes.
And the theory really sort of trivializes it.
Yeah, yeah. Sorry, this factor goes away, but this factor becomes Ising.
What is it actually?
This is just like, so this is actually not the standard gauge theory action because it's really just picking. Yeah.
So I was, I see it's a
this is,
link
yeah, this is link. That's why I'm calling link. Yes. So, yes. So that's what that's why I said this is, this look, yeah. Yeah.
Not a conventional.
Yeah. It's not, so that's why I was keep calling link model, actually. All right, so this gives basically the motivation for introducing ZPQ model. And let me see. So the second subject, and if you the reason why I want to introduce such models is that because if you consider models with both vertices and links, then there is a chance that you can find something which is actually self-dual. So now let's introduce ZPQ model. Which was introduced in this paper by a bunch of authors. And so now, I'm going to consider some model which have both degrees of freedom on the vertices, and I furthermore extend the Z2 Ising model to like a ZP models and ZQ model. So now the vertex degrees of freedom take p different value. So this is ZP. And there is also link variable, which I draw right Mij for each link, which takes value from Q. Okay, and so these variables, when you restrict P and Q to be 2, then these variables are basically related to the Ising model variable. So in the Ising, I had spin, which takes plus minus 1, and U, and the link model, I had a link variable which took plus minus 1. And that's going to be replaced with N taking value 0, 1, and M taking value 0, 1 in this new formulation. But basically, the relation between the two is something like this. Well, I haven't written. Yeah, I haven't written. I'm going to write it, of course. Yeah. And the interaction is basically the hybrid of the two interactions that I introduced already. And so the partition function of ZPQ model, which I also denote by ZPQ, is given by this expression. So let me just write it. ZPQ equals, of course, I need to sum over n's and m's. And I have this factor for each face, like in the link model. Let me first write the expression and explain the meaning of that. So there is some non-local constraint for the link variables m. And then there is, of course, the usual Boltzmann factor, which is basically a product of all possible links. And you have some potential, Ni minus Nj minus P and Ij.
You have these link and vertex variables, but
yes.
What were the S and U's?
Sorry. So this is just a relation to previous one. Because previously I was using +1 and -1, but now it's yeah.
Special case of this.
Yeah.
Or at least.
Yeah. For the special case of p equals 2 and q equals 2 corresponds to ZPQ model.
2, 0, 0, 2.
Yeah. In my notation, 2, 1 is the Ising.
2, 1.
Yes. And 1, 2 is the link model. And from this, you can already guess probably like what is the duality. Actually, the duality exchanges P and Q. All right, so this is the definition, but I need to explain a little bit more about what I mean by these expressions. So first of all, let me just explain what this is. So this is the analog of the non-local constraint we had, but now I have index Q, and this is defined in this way. So it's 1 if M1 plus M2 minus M3 minus M4 equals 0 mod Q, where for each phase and where M1, M2, M3, M4 is defined in this way. So basically, this is just saying that like analog of the field strength for each phase is 0 mod Q. And this Kronecker delta sets gives you 0, gives you back 0 otherwise. Mm-hmm.
Is this same as P-state Boxman?
Q to 1, yes, yeah. I think it goes, yeah. What's the model?
Exponent, what was that?
Yeah. So I didn't.
Some V of
yeah, V. Yeah, so actually there's some arbitrariness. So V, the only constraint requirement that I impose on V is that V is some periodicity. So basically, V is some potential term, and which is basically some periodic function. Yes? Well, as long as you can like tessellate it in terms of like a square lattices, then it also can be applied to higher genus surfaces.
Or higher dimensional lattice.
A higher dimensional lattices. That's a good question. That's a good question. Yeah.
If you take a translation to language of gauge theories,
yeah.
might be more
Right.
forward.
Yeah.
Sense, this is a Gauss constraint.
Yes.
Gauging variant.
Yes.
Thing which are written potential
Yes.
gauging variant.
Yes. Yeah.
Etc.
Yeah.
But the earlier one was not. The potential was just this Uij. It's not. No, you see, here's N and M here.
Yeah.
So I'm trying to understand in that language, can you think of that as a gauge? This one is certainly.
Right. So the previous one that seemed to be violating the gauge invariance was this factor. And indeed, there is actually some analogous term here, and you can, but because like you can really like this one is really a special
This
case.
wouldn't satisfy this translation.
Well, you mean this? It does, because u is like exponential, like -1 to m. So the relation between u and m variable is precisely this one. So it does satisfy. So like basically, typical way of satisfying this condition is to just put some like a cosine or sine, and this is actually some particular case, or cosine or sine exponential.
One thing of this action that for a pair of vortices, for example.
Yeah, it is.
Yes. It's also related to vortices. Yes.
Because Gauss's law is still being enforced.
Right. Yeah, locally I'm excluding vortices, and that's that. It's just that. But higher genus surface, like there is some holonomy. Yeah. And that's why this story is connected to the T-duality. All right, so let me just make a claim first. So the claim is that, as you already probably anticipated, the partition function of PQ model defined on the lattice is the same as partition function of QP model defined on the dual lattice. And the relation, but there is one transformation that you need to do. So you need to actually like change V to V twiddle, where V twiddle is basically the Fourier transformation of V. So if you have a V of UN, then what you need to do is to do the Fourier transformation. So this is the claim. And this transformation is basically the analog of beta going to beta twiddle, but now generalized to a more general potential. So let me now prove it. You mean like whether they are coprime or not matter?
For example, the Fourier transform
Yeah.
to get the independent of that.
Right. Yeah. Yeah, actually, that's a good point. Yeah, I didn't carefully think about it. So there might be, yeah. I think the safest choice is to make it coprime right now. And if it's not coprime, then there might be some some subtleties in the proof actually, but probably not. But I'm not completely sure. Okay, so let me just try to prove it. So the idea is to start from this model and then rewrite the partition function into this model. Okay, so and in order to do that, so I consider this lattice gamma and then introduce auxiliary variables living on a dual lattice. So I introduce auxiliary variable and twiddle living on the vertices of the dual lattice, and which takes value in ZQ. And I also introduce link variable on the dual lattice, which I denoted by ZA. And now link variable takes value in ZPQ. So far it's not yet like the QP model because a variable is taking value in ZPQ. So it can take from 0 to PQ minus 1. And so what I'm going to do with these variables. So I'm going to use this variable to re-express factors in these expressions.
This is in lattice, and you're looking at n lives.
Yeah, n tilde lives on a dual lattice. A also lives on a dual lattice. So so far I just introduced some variables, the relation whose relation to the original problem is unclear, but now I'm going to utilize those variables to rewrite both these factors. And the first thing I'm going to do is as follows. So let me just. The first thing I'm going to do is to rewrite this delta function constraint. So I had some delta function constraint, which is basically sum of m. And using the point is that this delta function constraint is defined for each phase. And for each phase, there is one vertex of the dual lattice. And you can actually express this delta function using by integrating in the variable on a dual lattice in this way. So I just do this. And this sits here. Right? And so this is, you can actually show that this is exactly equivalent to this. And the reason is because this is just a geometric sum, and if you do it, then you get this factor. And if you look at the denominator, then whenever this blob is integer, then it looks like a denominator always vanishes. But only when this definition can be finite only when I was talking about numerator, and only when the denominator also vanishes. So that gives you this like a delta function constraint. All right, so this is like a way to introduce or integrate in and twiddle. And I also integrate in a variable by rewriting this factor. So now this factor was defined for each link of the original lattice, and each link of the original lattice intersects the link of the dual lattice once. So there is one distinguished link of the dual lattice for each link of the original lattice, and therefore I can just do the Fourier transformation in this way. Over PQ and NA, and I just NI minus NJ minus P MIJ. Okay. Blob can also be multiple of Q, yes. Sorry? Yeah. Yeah. So
that is set Q, so multiple of
yeah.
Q is
Right. Yeah, M is from the beginning like it takes value in ZQ, so there is already identification.
this PQ, I didn't know. You have this PQ because you have this translational thing
Yes.
set by P. So why was it P
Right. So so the reason is n is a ZP variable, and m is the ZQ variable, and there is a p here. So it's just like a different way of parameterizing like a splitting PQ into
least common multiple.
Right.
That's where this
Yeah.
thing might come in about the
Yeah.
relatively prime or not.
Yeah. Yeah, indeed. Indeed, I didn't explain the meaning of this factor, but that's basically what's happening here. All right. So in this way, I basically introduce variables on the dual lattice, which is this one and this one. And after rewriting in this way, now everything sits in the exponent. So you have like a couples to these variables, and twiddle couples to this m variable. And the next step is to just integrate out the original variables. And let's first integrate out m's. So m is living here, so it couples and twiddle. And m is sitting here, so it also couples to a. So sum over m, and that so m is defined for the link, and for the link of the original variable, and this variable couple. And if I draw dual lattice, then this variable couples to the n twiddle sitting here, and n twiddle sitting here, and also variable a sitting here. Okay, and if you just keep all the possible terms that that couples to particular m variable, then what you get here is this. Okay. But this is precisely the definition, or sorry, not the definition, but this is precisely the formula that I already had here, up to like a trivial factor of 1 over q. So by doing this sum, now I have some delta function constraint on this variable, which is n twiddle I twiddle minus n twiddle j twiddle minus a I twiddle j twiddle. So which basically tells you that this combination must be 0 mod q. So therefore, you can actually solve the constraint by introducing yet another variable in this way, q times yet another variable m twiddle in this way, right? And so this new variable, so original variable was taking value in ZPQ. And because there is an overall factor Q, I can restrict the range of m twiddle to be ZP, to be inside ZP. So here there might be some subtleties in when P and Q are not prime. Yes? Yeah. Yes. Yes. Okay, sorry.
saying that this constraint can be solved by demanding
Yeah.
locally the
Yeah. Right. Locally, you can define, but like this is just like a local constraint, so you can really just like locally define what M twiddle is. And but the subtlety, well, the possible subtlety is that like using the fact that A is taking value in ZPQ, I would just restricted the range of M twiddle to be ZP, but this might be subtle if P and Q are not relatively prime, but I think it's probably okay, but I haven't thought carefully about it. All right, so now I'm basically done with integrating out M's and basically replaced A's with N twiddles and M twiddles. So I'm done with this part, I'm done with this one, and the remaining one I need to do is to summing over original spin variable, which is Ni's. So what I need to do is to just like substitute A with the expression that I wrote there. And if you do so, because A is given by N twiddles and M twiddles, that gives you a coupling between N twiddles with N and M twiddle with N. But so now N can potentially couple to N twiddle and M twiddle. But it turns out the coupling between N and N twiddle vanishes if you carefully think about it. So let me just briefly give you an idea why it is so. So N was defined for each vertex of the original graph, and N twiddle was defined for the vertices of the dual graph. And the coupling between N and N twiddle came from the coupling between N and A, where A was defined for the link of the dual lattice. And if you carefully follow the procedure and replace A with N twiddles, then you see that in this particular case, let's call this N twiddle 1, N twiddle 2, N twiddle 3, N twiddle 4, then the coupling induced by that replacement turned out to be of this form. And there is one more term. And from this structure, you can immediately see that this coupling actually just sums to 0. And roughly speaking, the continuum analog of this mechanism is that if you have this kind of coupling, then you can, on a closed surface, you can just like do the integration by parts and then write it in this way, which just vanishes because of the antisymmetry of epsilon tensor. So what I was saying is that the coupling between N and N twiddle just becomes 0. And then what you need to worry about is the coupling between N and M twiddle. So now let's again write this graph. So N was now living here, and M twiddle is now living on the dual lattice, but now on links. So you have M twiddle 2, M twiddle 3, M twiddle 4. And then it turns out the sum is again given by this familiar expression. Yeah, well, this is probably not super important, so let me just erase it. So, familiar expression, which is, again, of the form of the field strength. Now on a dual lattice. So then you can just like integrate out or sum over NP to get now the conserving delta functions, plaquette condition for the delta function. Now for the dual lattice, and the condition is imposed on M twiddle. So now if you collect everything that's left, so the one term which is basically delta function, and the other term which is, okay, it's still here.
Delta function is 1 by q or so. Converting these exponentials to delta function are 1 by q factors.
Right. Yeah. Actually, yeah. I'm basically like neglecting all the trivial factors, but you of course need to, like, if you want to be precise, you need to keep track of them. Okay, so essentially what we are left with is this factor and this factor, and A is, as I wrote over there, it's given by some n twiddle minus q times m twiddle. Then you can clearly see that this is already of the form of the original action that I already wrote. And okay, now the blackboard is getting a bit messier, but the conclusion is that by doing this, you can basically show ZPQ model is equivalent to ZQP model, now defined on a dual lattice. So then the conclusion is ZPQ. Okay, so let's see. Maybe it's a good time to stop, or what do you think?
Yeah, to 1, I think.
To 1, okay. So maybe, okay, maybe then let me just briefly discuss the relation with the T-duality in string theory, and then tomorrow I'm going to discuss the generalization to the random lattice and random graphs. Okay, so but before doing that, is there any questions so far? Yeah. I think so, yeah. All right, so far I've been discussing some funny duality. Let's see. Yeah, I think it was. Yeah, I think the T-duality is mentioned. Yeah, explicitly mentioned in that paper. Yeah.
Are there, I mean, just out of this thing, I mean, just like the Ising and so on have condensed matter realizations too. Are there realizations, at least in some actual systems, things, and or even the critical behavior of these systems?
Actually, yeah, I see.
You know, the 2D
right.
corresponding to that.
Yeah.
Is there this thing of DQ behavior where related to some?
Okay, so in terms of as for the critical behavior, the detail of this PQ model might not really matter actually, because on a spherical Riemann surface, you can actually argue that this ZPQ model, ZPQ model is the same as ZPQ model. It's just like a spin of object taking variable PQ.
Some kind of.
No. So this is the model that I introduced, but this is P times Q.
So it's like
It's a pulse mode. Yeah. Yeah. So essentially, if you're just interested in the critical behavior, I think you can just use the critical exponent of this model.
Critical behavior is always
Yeah. Yeah, on a sphere.
This is generalization of some topological differences. Is that how we should think about it?
Yeah, I think
The
so.
the spectrum of topological operators are different.
Yeah, I think so. Yeah.
And some new defects.
Right, I think so. Yeah.
So it's PQ corresponding with some defects.
Yeah.
So the topological sector on
Right.
hydrogen is
Which the defects are like given by some Q or something or
Yeah.
So they are some kind of
Right. Yeah. Yeah, I think it's indeed interesting to try to understand this model from that perspective, but I don't think that's done much.
I guess
At
if
least.
you have a CFT interpretation of some vertex operators, and then
I see. Yeah.
some statement about what vertex operators are.
I agree.
So that would have been, but most of them are non-unitary, whereas this would be unitary.
It's all positive sign.
Yeah, so you shouldn't confuse this with like a PQ minimum model, although I'm using the same PQ. Okay, so this was the definition of the model and the property of the model. So let me just briefly discuss the relation with the T-duality by briefly reviewing the derivation of the T-duality in compact boson. So there is like one passive integral derivation of the T-duality of the compact boson, which is often called like a Bush's prescription or Bush's rule. So now here I'm dropping like O2 pi or alpha prime factors. And this model, by integrating in extra variables, you can just rewrite this action in this way. This is just like a trivial rewriting. And, sorry, I need minus sign here. And if you perform the integration by parts to this term, then you might say that, okay, so this is also the same as this action, which is x times del a bar minus del bar a. But the reason I put the question mark is that this is not really correct, especially again on higher genus Riemann surfaces. And the reason is because, so suppose you again consider a torus. But you need to remember the fact that x can actually jump because there is some identification. So one way to use the Stokes theorem is to cut this torus in this way and then just like open it up into a rectangle. So now I have some boundaries here and then apply the Stokes theorem. So then indeed, then apply the integration by parts. Then indeed I get this extra boundary terms times plus this term. But the point is that normally, if the fields are single valued, then this term, this boundary term cancels out because this term and this term just have like opposite sign. But the point is that because of this identification, the X field living here and X field living here can differ by multiple of R. So this basically tells you that in path integral, if you want to perform this kind of like integration by parts, then you need to add extra summation, which takes into account this extra integer here. So now, let's just write this action S prime, and now the action is e to minus S prime, but in addition, I need to sum over integer, and I are basically where A is coming from this variable. Okay? So this is basically the boundary term that you need to include when you do the integration by parts. And this, the cycle integral of A is defined for each non-trivial cycle of the Riemann surface. And for each Riemann non-trivial cycle, I introduce integer ni and sum over integer ni. Okay? So now, in this form of action, I can try to integrate out the original variable x, and then some new extra variable ni. So that gives you two different things. The first of all, integrating out x basically gives you, because this is basically the Lagrange multiplier for this factor, so this gives you some delta function, which basically sets the field strength to be 0. And in addition, that sum over r basically gives you that, sum over n gives you that this Wilson line for each non-trivial cycle must be 1. And so from this constraint, you can locally solve A and A bar in this way. But you need to remember this x twiddle cannot be defined globally, and there can be some jumps. But jumps or discontinuity is actually constrained by this condition. And if you carefully think about it, then you realize that the constraint for the jump or the discontinuity should be of this form in order to satisfy this condition, where m is now another integer. From this, you can easily see that now you have new action, which is basically del x, del bar x, twiddle, if you put it here. But now new variable x twiddle has periodicity, which is like 1 over r instead of r. So this is like a simple path integral derivation of the T-duality. And then, but if you compare this derivation with the derivation of the ZPQ model, then it's clear that there is some nice analogy. And roughly speaking, these x variable played a role similar to n variable or n twiddle variable. And remember, in the derivation of the ZPQ model, by summing over n, you get some non-local like Plackett delta function condition, and that's also the case here. And roughly speaking, this gauge field A is small a that I introduced in the proof of the duality of the ZPQ model. And if I were to make things more, okay, so another comment that I can make is that basically considering a compact boson is like first considering non-compact boson and just like make a lot of small segment and then identify points here and points here. So this is also something that I did in that PQ model. In the PQ model, so remember the potential term had this form, E times Mij, and these are ZP variable, and these are ZQ variable, and the V had a periodicity of PQ. So this basically, what this is doing is that, suppose you have a PQ number of points. So let's say 1, so 0 to p minus 1. And what I'm doing here is that I'm basically introducing two variables. One variable which, so the total number of points is PQ, and Q in this case is 4, because you have 4 regions. And I'm parameterizing this whole circle using two different variables. One variable is an ice, which basically like describes the difference within one patch. And another variable is something like a winding mode, which allows you to go from one patch to the other patch. And this is the reason why I'm calling it winding is because that's precisely winding in this continuous model. So if you do after doing this identification, I can consider some mode which goes from one patch to the other patch, or one patch to the next patch, and that's precisely the winding mode. And the only weird thing about the PQ model is that, first of all, space is discretized. And in addition, I'm putting some cutoff in the winding mode, because in the continuous model, I can take a winding mode to be arbitrarily. But in the PQ model, there is a sharp cutoff of the number of winding modes. So in this sense, this ZPQ model is precisely the discrete analogy or analog of the T-duality. But so far, I've been discussing about like a duality on a fixed lattice, and then like tomorrow, I'm going to talk about generalize this duality to random lattice, series on a random lattice. And thank you very much.